Hello Math 2413 students. Let's begin lesson 6, Implicit Differentiation. Let's go to section 1, subsection 1.1, Implicit Relation. What is it? Does anybody recall what an implicit relation is? Anyone? Nobody? How about a relation then? What is a relation? Do you recall that? We went through that in college algebra or even before. A relation is a subset of a Cartesian product. Remember that? Any subset will do. Of course, this is a math course, so we are not interested in just any subset. We are interested in the kind of examples that are associated to some mathematical equations, like this one, or this, or here's a third example, that. Of course, there are many more, infinitely many more. In any case, these are the kind of examples that we are interested in. And please note that these are all given by implicit equations. A relation determined by an implicit equation is called an implicit relation. So these are all implicit relations. In case you don't already know what an implicit equation is, here's a reminder. This form, as I just highlighted in green, those are implicit equations. X and y are intertwined and the right-hand side is constant. Here's a prime example. Expression of x comma y, and then the right-hand side is constant 1. How about the next example here? Is this an implicit equation? Yes, it is. If I subtract y, this 2xy to the other side, then you're going to get an expression of x and y equals to some constant 0. So yes, this is also implicit. And then how about this one? Well, that left to the students. In contrast, these kind of equations are called explicit. Y equals to f of x form, y is a function of x, or x equal to g of y form. X is a function of g. X is a function of y, excuse me. In any case, an explicit equation has a direct connection to functions. In contrast, implicit equations do not have direct relations to functions. Indirect relation maybe, and excuse me, I shouldn't have used the term relation there. We are talking about relations here, implicit and explicit relations, and suddenly I use the same term relation in common English sense. So explicit equations have direct connections to functions. Implicit equations do not have direct connections to functions. Connection or association, whatever. I shouldn't have used the term relation here. Oh boy, it's often difficult to speak like this. Sorry, it's the nature of mathematics. It's really hard to communicate without the terms that are already taken away by mathematicians. Sorry, this is the nature of mathematics. Sorry again. I mean, communicating or speaking mathematically correct is often as difficult as speaking politically correct. Sometimes even worse. Anyway. Sorry about that. I got a little bit carried away after misspeaking this. Anyway, let's come back to this. The key point here is implicit equation versus explicit equation. And then they give rise to implicit relation and explicit relation, respectively. Now, explicit relations are basically functions. So geometrically, they're going to give rise to graphs. Right? How about implicit relations? Well, here's an example. This visualizes the set of all points x comma y that satisfies this relation, x squared over 9 plus y squared over 4 equals to 1. This kind of curves are called implicit curves, a curve given by an implicit relation or implicit equation. And clearly you can see that this is not a graph of a function. It fails the vertical line test. It also fails the horizontal line test. So switching x and y will not solve the problem either. Here's another example. This example is called Descartes' volume, named after French mathematician and philosopher Descartes. And then this came from this implicit relation, set of all points x, y that satisfies this relation. And you can clearly see that this also fails the vertical line test and horizontal line test. So either way, y equals f of x or x equal to g of y, either way it's impossible. So this is not an explicit relation. So not a graph of a function either way, x or y. How about the third example here? Oh, this is even worse. We have two curves. In fact, this is commonplace. If your relation is more complicated, yes, you can clearly see that this is more complicated. This is fifth degree, quintic order. And this one is cubic, only third degree. And this one is quadratic, only second degree. So this one is far more complicated. And as you can see, the graph is more complicated here either. And of course, you can create even more complicated equations using some transcendental functions like trigonometric functions and things like those. In that case, you can easily create examples with infinitely many curves. So yes, one relation defining multiple curves, that's commonplace for implicit equations. Consequently, the calculus technique that applies for implicit equations will be a little bit more complicated and a little bit harder than the kind of techniques that we have been applying so far. They're all for explicit equations. So how exactly are we going to do that? That's going to be the topic for the next video. We're going to study implicit differentiation there. For now, let's come back to this 1.1 and let's talk about some additional topic. Now this one is not for everybody, so there may be a lot of students who may want to stop here and just skip. That's going to be okay for the majority of the students, I think. If you're in a teacher track, then this is going to be necessary. Yes, analytic geometry is a big part of Texas exams, so that's necessary. If you're going over to Calculus 2, pay attention here because this is essential there as well. All right, let's come back to this. I gave you sufficient warning, so if you don't like this, you can just stop and skip at any time. Come back to this. All right. In this particular case, it is not too difficult to solve for y and get an explicit expression. In fact, here's the answer key. In my answer key, I did it in a little bit more complicated, a little bit more general way. It's not necessarily more complicated, a little bit more general. And that kind of general technique is necessary for analytic geometry. So let me rewrite this relation in a little bit more general form like this. X squared over a squared plus y squared over b squared is equal to 1. Compare that. You can clearly see that this is a special case. A is 3 and b is 2. And look at the picture. Not coincidentally, horizontally, we go from -3 to +3. Vertically, we go from -2 to +2. So major radius in horizontal direction, x direction, is 3. Minor radius in vertical direction, y direction, is 2. And that's why we have 3 squared and 2 squared like those. And those are something that you go through in analytic geometry. And conic sections are important for the students in math teacher track. So please review this. We went through this in pre-calculus, but unit analysis is a bit weak on pre-calculus, so the review is up to you. Okay, from here, let's solve for y. How do you do that? Well, here's the answer key. It's not too bad. You're solving for y, so that's what you want. So flip the other term to the other side by subtracting away. So subtract this x term to the other side, and then remove this denominator by multiplying away. So multiply away this b squared, then you get b squared times the previous, and that's how you get y squared equal to some expression. Now, final step, take the square root. And then voila, what do we have? We have an explicit equation. Actually, two explicit equations. Positive square root, blue, and negative square root, red. Positive square root gives me one function, and whose graph is visualized here, up there in blue, and a negative square root gives me another function, and that graph is down here, highlighted in red. So in this case, in this particular case, it wasn't too difficult to solve for y and get a pair of functions, a pair of explicit relations, and then we can apply all those calculus techniques. We can take the derivative and things like those, find the rate of change, slope of tangent line, equation of tangent line, all kind of things. Linear approximation, whatever. Because we have the chain rule, we have product rule, we have quotient rule, whatever, we can do all those kind of things here. In general, however, that's not possible. Or theoretically possible maybe, but practically impossible, as you can see from the second example here. Okay, in this case, what do we have? Well, we have these curved pieces. Blue is one, red is another, green is a third, and then purple is the fourth, it seems. As a matter of fact, however, we can put blue and red together as one function, and then green as the second function, and purple as the third function. And if you want to see those algebraic expressions, okay, go ahead. They're right here. First line is the first function. Second line is the second function. Third line is the third function. What do you think? Do you like those? Do they make sense to you? To me, they're meaningless. Yes, of course, theoretical solution exists, and then if you use computer algebra system to find those, you can use computer algebra system to calculate the derivatives and do all kind of things. So theoretically possible, yes, but practically it's as good as impossible. Still, to a certain degree we can do that, and that's how we got the color coding. Blue and red as the first function, green as the second function, and purple as the third function. So theoretically, at least, we can apply some calculus. Take the derivative using chain rule, product rule, quotient rule, whatever. In some cases, however, even that fails. Theoretical solution, not even that. In this case, we have a quintic polynomial expression, fifth degree. In this case, algebraic solutions do not exist in general. It is a proven fact. So even theoretical solution does not exist. Excuse me, theoretical solution, I should have said algebraic solution. Algebraic solution does not exist. Theoretically, okay, if you just want existence and no way to actually calculate or express precisely, then yes, it may be possible to bring this down into 5 pieces and work something out. But nobody can do that. It's proven that nobody can do it. In short, all those techniques we learned for explicit expressions from lesson 1 to lesson 5, they're all thrown out of window, and we have to rely upon the new technique, and that new technique is the implicit differentiation technique. That's the topic for the next video.